When we think about kinematics, the first great tool that we have are the equations. But there's another very important tool, which are the motion diagrams. So let's start with what is a motion diagram. So I have two of them up here. This is a displacement time graph, and this is a velocity time graph. And the idea is we're going to plot what the displacement of some situation is as time changes, and here we'll plot the velocity as time changes of the same situation. And they may be similar looking or they may be different looking depending on what's going on. So let me say a couple of example situations and we'll plot those there. So here is a person walking at 3 meters per second. So that's the situation. So we can depict that as a distance graph and a velocity graph. We could remember that velocity is distance over time, or distance is velocity times time. So basically, velocity is constant and the distance is going to be increasing. So after 1 second, this person's going to walk 3 meters. After 2 seconds, it's going to walk 6 meters. So I can even put numbers on here. It's going to be at 1 second, 3 meters, 2 seconds, 6 meters, and so on. So the displacement time graph looks like this. This is going to be a straight line. So the velocity time graph is going to be also a straight line. But here we say the velocity is 3 meters per second for the whole time. So we're just going to draw a straight line that's flat at 3 meters per second. And that's it. This line here represents the displacement, and this line here represents the velocity. The best way to improve your grade is with a practice test. On my site, I have a kinematics practice test for free. Click the link below to get it today. Let's imagine there's another person standing there, and their velocity is 0. They're just standing, but they're standing 3 meters away from the starting point here. So we call this displacement equals 3. So this point there is defined as displacement equals 0. Let's draw the motion diagrams or non-motion diagrams for this person. Basically, we're saying they're standing at 3 meters away from the original point there. So the displacement is a flat graph, and the velocity just equals 0. So we draw a straight line across v equals 0. Like that. And that's it. So we have displacement and velocity for this person standing. Okay, let's introduce the third one. We have displacement, velocity, and also acceleration. All right, so now I have 3 motion graphs, one for displacement, one for velocity, and one for acceleration. And now we're going to depict all 3 of these things for one situation. So let's imagine there's this person and they're holding a ball and they throw it upwards. So what's going to happen to this ball? It's going to go upwards until at the top there, the velocity equals 0. We can even calculate how long it will take to go to the top there. So let's just do that. Let's try and figure out what the time is using the kinematics equations. Remember, we begin by writing down the 5 variables. Velocity initial here is going to be 12, and v final here is going to be 0. So what's acceleration? Acceleration is going to be negative, and that's negative 10. So how do I calculate the time? The right equation is going to be Vf equals Vi plus At. That one there. So I can plug in my numbers and calculate what time is going to be. I get 0 equals 12 plus negative 10t. Move 12 over. I get negative 12 equals negative 10t. Divide by negative 10. I get 1.2 is going to be the time. Okay, very good. So now it's going to be very easy for me to draw a velocity graph. So on this graph, I'm going to start at time is 0 and go to time is 1.2. At time is 0, the speed was 12 meters per second. And at time 1.2, it was 0. So I'm going to draw a straight line. So what's this saying? This is saying that the velocity is decreasing, which makes sense. At the beginning here, the velocity was 12 meters per second and is going slower and slower until at the very top there, finally the velocity is 0. As time increases, the velocity is getting smaller. How about the acceleration? Well, acceleration is constant. That is, acceleration equals negative 10 meters per second squared all the time. So I just need to draw a straight line for acceleration at negative 10 meters per second squared. So there, the acceleration is going to be negative 10 meters per second squared for the ball always. How about distance? I can actually calculate distance as well. I need to do some more kinematics equations. If I have these numbers, I could use VF squared equals VI squared plus 2AD to calculate the distance. There it is. So I'm just going to put in the numbers. So I get 0 equals 12 squared plus 2 times negative 10D. So I'm going to take negative 144 across. And I get D is 144 divided by 20. So D is 7.2 meters. So D starts at what? 0, and it's getting higher. So the distance is increasing between 0 and 1.2 seconds. So at time is 0, the displacement is at 0. At time is 1.2, we're going to get to 7.2 there. Now, you may be tempted to, at this point, draw a straight line and say that the distance is increasing, but that would not be correct. It's actually going to be shaped like a parabola. Not the most pretty parabola around, but it'll do. So what's going on here is that the velocity is changing. So at first, the distance is changing pretty rapidly, but as time goes on, it's slowing down. So what's happening is the curve is getting less steep. It's steeper here because it's traveling faster, and shallower here because it's traveling slower. This is the effect of acceleration. Acceleration is acting on the ball, and it's making the distance change. Or to say it another way, acceleration is acting on the ball, and it's making the velocity change. And the rate of change of displacement is changing. That is to say, the velocity is changing over time. And what ends up happening is a curviness on the displacement. Here's the general rule for these motion time graphs. If acceleration is 0, then the velocity is flat, and the change in displacement will be linear. If there is acceleration and it's not 0, then the velocity will be changing like a linear graph, and the distance will be curvy like a parabola. So let's just do a simple example of that. Let's imagine a situation where acceleration is 0. So this might be a car moving, this might be a person walking, this could be anything where acceleration is 0. In this case, the situation could have a velocity. Maybe it's 4 meters per second, but it's going to be some flat velocity where the velocity is not changing. When velocity is constant and acceleration is 0, displacement changes with a linear graph. Like that. Now let's draw a situation with acceleration. So let's imagine something with acceleration. Maybe this is a car with somebody, their foot is on the gas and the car is accelerating. Maybe this is somebody sprinting and they're starting at the beginning of a race and they're trying to go as fast as they can. Something where there's acceleration. So here, the velocity is going to be changing. I call the acceleration positive in this situation. So velocity is going upwards. It's starting slower and getting faster. So when acceleration is flat but not 0, some real acceleration, then velocity is going to have a linear graph that's increasing. And displacement is going to be an upward shaped parabola. So the idea is you're getting faster and faster, and as velocity increases, the curviness of the displacement is increasing. And this kind of makes sense if you think about it. If you're in a car and you got your foot in the gas, at first you're not going to go very far. but the more you go, the faster you're going to get because you're accelerating and you're getting faster and faster. This parabolic relationship between acceleration and displacement is actually captured inside the kinematics equations. This one here, d is vit plus 1/2 at squared. So let's imagine, for the sake of simplicity, that for a second that the velocity initial is 0. So this is like a parabola. D equals 1/2 at squared. And t is like my x term. So the distance depends on time in a parabola kind of a way when acceleration is not equal to 0. You've probably done something like this in pre-calc, graphing parabolas, y equals ax squared. So the displacement is my horizontal y, and my time is like my x there. And when there's a number here, when there's acceleration, displacement is going to be like a shape like a parabola. Let's just do another example situation to help you think through this more. Here's a person at the top of a cliff with a ball, and the person throws the ball downwards. Let's say the ball has an initial velocity of 5 meters per second, and the cliff is 7 meters high. Let's depict this situation with the motion time graphs, and we're going to begin by calculating the numbers. So let's calculate for v final as well as for time. Let's start with the list method. So I can write down what I know. I know the initial velocity, the acceleration, and the displacement. Initial velocity is 5, and acceleration is going to be 10, and it's positive 10. In this question, I'm going to be setting downwards direction as positive. Velocity initial is downwards, and acceleration is downwards, so they're both positive. And the displacement is also downwards, so it's also positive 7. We set this as the initial displacement as 0, so downwards is going to be 7 in the positive direction, which is down. So 7 positive for displacement. Let's begin by calculating the final velocity. We're going to use vf squared equals vi squared plus 2ad. That's the right equation. Let's plug in the numbers. I get vf squared equals 5 squared plus 2 times 10 times 7. I get vf squared is 25 plus 140, that's 165. If I take a square root, I get an answer for final velocity. So it's 12.8 meters per second is final velocity. Great. We can also calculate the time. I'm going to use vf equals vi plus at to calculate the time. We're always a little bit happy when we see this easiest one, so we can plug in some numbers through that. We get 12.8 equals 5 plus 10t, so move 5 over. So we just need to divide by 10. We're going to get time is 0.78 seconds. So I'm going to put that number on the list as well. Okay, so I've calculated for all the possible variables in kinematics for this situation. Now let's draw 3 graphs: displacement time, velocity time, and acceleration time. Here are 3 graphs. I've labeled them displacement time, velocity time, and acceleration time. I've tried to label them a little precisely. So I've got some time markings, and they're going to be equal, they're going to be parallel to each other. And there is some markings for the numbers for displacement, velocity, and acceleration on there. So we're going to take the information from this situation and put it on there. And I should just say at this moment, so these 3 graphs are all depicting the same thing. They're all depicting this one situation, but they're telling us about different aspects. This one's telling us about displacement, about velocity, and acceleration. And one of the things we do in physics is kind of separate these things so we can think about them separately and see what their relationship is to each other. Now, we've already said that when there is a constant acceleration, velocity is going to be linear and displacement is going to be parabolic or curvy. So we're going to try and capture those things in our graphs. The easiest one is to draw acceleration, so we'll start with that. It's a constant acceleration at the number 10. So there's my acceleration. It's 10 meters per second squared, and it's always the same. Remember, we've defined downwards as the positive direction for this question. So acceleration is down, so it's positive. So it's always positive 10 meters per second squared. we think about velocity, we have a number for initial velocity and a number for final velocity. So we should put the initial velocity at time is 0 and the final velocity at this 0.78 seconds. So my first point on the velocity graph is going to be here. Velocity is 5 meters per second and time is 0. The next one's going to be over here, which is the final velocity. So at this time, 0.79 seconds, that's when the velocity is 12.8. So that's the initial, that's the final. To draw the graph, I need to remember that here velocity is going to be linear. So I just draw a straight line connecting the two dots. Very good. And now for displacement. The initial displacement, when we're up here, we call that 0. So the displacement is 0 at time is 0. Like that. At the final time, 0.78 seconds, displacement is 7 meters. So I'll draw that point on the graph. So 0.78 seconds and 7 meters. Remember, time is like my x coordinate. Displacement here is like my y coordinate. I put displacement on the vertical and time on the horizontal. So I just need to connect these 2 points. And as I connect them, I'm going to make it curvy like a parabola, because when we have constant acceleration, displacement is shaped like a parabola. And there we go. We can see the displacement is changing at a changing rate. The slope is changing because the velocity is changing. Again, these 3 things are both telling the same story, but the same story from a different point of view. The displacement, velocity, and acceleration point of view. And this is a nice example of when we have a constant acceleration, our displacement is like a parabola. So in this chapter, Kinematics, we have 2 great tools to understand and analyze physics and motion. The first tool are the kinematic equations that we've looked at already, and the second tool are the motion time graphs. And when we put them together, we're really doing the physics thing, grappling with what's going on in different situations. This idea of depicting the 3 variables on separate connected graphs is an important one for physics. What questions do you have about this? Please write any questions below. I read all the comments and I'll answer the questions. The best way to improve your grade is with a practice test. On my site, I have a kinematics practice test for free. Click the link below to get it today.